Question number 71. It includes so much stuff. This is a delectable problem. We have 4 questions in this. We need to determine the velocities of the 2 objects, so that's 5 technically. Determine the velocities of the 2 objects just after the collision. How high up the track does the 0.5 kilogram travel back after the collision? How far away from the bottom of the table will that land, given that the height of the table is 2 meters? And then how far away from the bottom of the table does the second one eventually land? This one is at rest. M1, having fallen through H1, will have kinetic energy collide with this one, and it will collide elastically. Because the collision is elastic, this one is going to start falling down, that one is going to bounce back up, and then fall down. And since this surface is frictionless, no energy is lost. It's elastic, so energy is the same as it was before the collision. Let's look at what we have. This right here has initial gravitational energy, which will then turn into final kinetic for that object 1 right before the collision. So we can figure out velocity right before the collision. That's our first step. Let's find it. So mgh initial should be equal to mv final squared over 2. Masses cancel. V final, you probably know it by heart by now, is 19.6 times height. That is how we're going to figure out the velocity of m1 or speed of m1 right before the collision. 7, how convenient. So 7 meters per second, I'm using 9.8, not 9.81. So 7 meters per second is the velocity of m1 right before the collision. That is their approach speed. If you remember about elastic collisions approaching equals separation. I also know that I'm just going to use the 0.5 for mass 1 times that 7 should be equal to 0.5 times v final 1 plus 1 times v final 2. One equation, 2 variables, unsolvable. Let's do approach separation. 7 is their approach velocity, should be equal to v final 2 because that's to the right, minus v final 1 because that's to the left. After either one of them, doesn't matter which one I replace with which. This one is already easy. V final 2 is just 7 plus v final 1. Then I have my 0.5 times 7, so make the substitution for this. So 3.5 equals 0.5 v final 1 plus 7 plus v final 1. That is 1.5 v final 1. That is negative 3.5 over 1.5. Gets me negative 2.33 meters per second. So the bounce velocity of the first one is negative 2.3 meters per second. Okay, 2.33 for sig figs. Then I plug it into the separation velocity. So v final 2 then going to be 7 minus 2.33. So that's going to be 4.67 meters per second. That's the velocity of mass 2. A, determine velocities of the 2 objects right after the collision. M1 has v final negative 2.33 meters per second, and M2 will have the velocity final of 4.67 meters per second. All right, that's our first set of answers to A. B, how high up the track does the 0.5 object travel back after the collision? Well, if it has 2.33 meters per second, remember mgh final is going to be mv squared over 2 initial technically, because when it bounces back, and that's your 2.33. Masses cancel. H final is going to be 2.33 squared over 19.6. That is 0.28 to 0.27. That's your answer to B. Then we're going to solve for how far away from the bottom of the table does the 1 kilogram object land. So if the table is 2 meters. So remember, time in the air is going to be the root of 2 change in y over g, and that's going to be the 4 over 9.8. 0.6399 seconds, and then our x is going to be 0.639 times the 4.67, because that was the speed with which our M2 was moving after the collision. I get 2.98 meters. That would be our answer to question C. Question D, how far away from the bottom of the table does the 0.5 kilogram object eventually land? Because this surface right here is frictionless, it goes back with 233 and rolls back again with 233. So it's the same time, which is 0.639 times the 233, the second one is going to land 1.49 meters away from the edge.